Hey everybody, welcome to lesson number 4, the binomial theorem. So let's start right off by looking at some binomials, which we see these binomials would be x and y on one side, and we have a power. On the other side, we have the expansions. And this is really going to help us work with the binomial theorem, these expansions, because we have a couple of things that we want to take notice of. So I want you to take a second to copy this down, and then we're going to discuss these right after. All right, so 4 things that we should be able to notice about the expansions, right? First of all, we have x plus y to the power of 0, to the power of 1, power of 2, 3, 4, and 5, and so on. So this is going to go on infinitely. And you notice that we have these expansions over here. Something that we can take notice of is that each expansion has n plus 1 terms, n being the power here. So, for example, if our n value is 0, we still have 1 term here. If our n value is 2, we happen to have 3 terms here, right? The power is 5, we would have 6 terms for that expansion. Okay, so that's something good to know. Second, the powers on x and y are symmetrical. Specifically, x is going to decrease as y increases. For example, if we look here at the third expansion, right, we have a power of 3 on x, and it goes down to 2, power 1, and then no power at all, 0. And if we look at y going this way, right, we have power of 0 on y, which is why it's not here, power of 1, power of 2, power of 3. Right, so if we look heading in on x and on y, they're symmetrical, right? So that's something we just noticed here. Third thing we can notice is that the sum of the powers on a term is equal to n. Let's take a look at this expansion here, the fourth. Right? We have a power of 3 and a power of 1 for x and y. When we add those, that gives us a power of 4. Right? 2 and 2 for x and y. We add those, we get 4. So it doesn't matter where in this expansion, if we add those powers, it's going to give us back our n value. And finally, the coefficients are symmetrical. That is going to be useful in the future. Okay, I'm going to look at this fifth expansion here. Anything that's missing, we assume to be a 1. So we notice that on both sides there's a 1, and then we have a coefficient of 5, and then a coefficient of 10, right? So it's symmetrical on both sides, and it happens here as well, right? So those 4 things we want to keep in mind when we're working with the binomial theorem. But before we can even get to the binomial theorem itself, we have to talk about something called factorial. Okay? Factorial is just the product of n and all positive integers before n. Product meaning multiplication. So we write that with a little exclamation mark. That means factorial. So if we're going from n, we're using n itself and then every number before it, right? 1 before n, all the way down to 1. And then there's something important that we want to note right here, is that 0 factorial is equal to 1, not 0. That has to do with set theory, right? Even if we have a set with nothing in it, it's still considered to be one set. So when we look at factorials, if we see 0 factorial, we still have 1 rather than nothing, because there's still something there. It's just empty. Okay? So we're going to look at how some of these factorials work. So if we're doing 5 factorial, we're doing 5 times every number before it. So times 4, times 3, times 2, down to 1. So we're multiplying all these numbers. And if you want to grab a calculator to do this, you can. Some calculators actually have the factorial button, so you can check it that way. But if we multiply, that gives us 20, times 3 is 6, times 2, we get 120. We can also do these with non-numbers, right? We can do it with variables as well. So if I'm working with n plus 2, the number that comes before n plus 2 would be n plus 1. Right? That would be 1 prior to 2. And then if we were to multiply the number before n plus 1, that would be plain old n. And then we could multiply n minus 1, because that is one number before n. And we can keep on doing this, multiplying all the way down till we get to 3 times 2 times 1. Okay, so we don't know exactly how many there are because we don't know where n starts, but these are all the numbers that we would be multiplying all the way till we get to plain old 1. Okay, so that's how factorials work. Let's look at an example of one using some substitution. Okay, we want to write the first four terms of an equals 3 to the power of n over n factorial. So if we do a of 0, we have 3 to the 0 power over 0 factorial. Anything to the power of 0 is 1. 0 factorial we know is also 1, so we get 1 out for our first digit. If we do n equals 1, we'd have 3 to the power of 1 over 1 factorial. 3 to the power of 1 is 3 over 1. So our second term we get 3. It's going to get interesting in the next couple. Right, if we do n equals 2, we have 3 to the power of 2 times 2 factorial. 3 to the power of 2 is 9, and then we're doing 2 times 1. This is just going to end up becoming 9 over 2. And our final one, 3 to the third over 3 factorial. 3 to the third is 27, and then we're multiplying by 3 times 2 times 1. Now, at this point, if I can reduce, I'm going to. And we're going to definitely want to do that in future problems as well. So I see a 3 that I can cancel out, and this 27 is going to end up becoming 9, right? Because 3 goes into 27 9 times. So what are we left with on top? We have 9, and on the bottom we have 2 times 1, which is 2. So here are the first four terms. 1, 3, 9 over 2, and 9 over 2. Okay, you have a problem that you're going to try right here. You're writing the first four terms. Remember, you're starting at 0. So pause this video and resume it when you're ready to check. Okay, let's see. So if you did a to the 0, you would have had 0 plus 1 over 0 factorial. That's 1 over 1, so you get 1 out. If you do a 1, you're going to be doing 1 plus 1 over 1 factorial, so 2 over 1. That's just plain old 2. The interesting ones are going to start showing up here. If we do 2, that's going to give us 2 plus 1 over 2 factorial. So on top we get 3. 2 times 1 is going to leave us with 2. And our last one, we have 3 plus 1 over 3 factorial. So that's 4 over 3 times 2 times 1. Here's where I can start doing a little bit of eliminating, right? That 2 and the 4 will reduce. So what I have here is 2 on top. 3 times 1 is 3 on bottom. So here are our solutions. 1, 2, 3 over 2, and 2 over 3. Not bad, right? Pretty easy to work with. Simplifying, I think, is even easier than that. It's a little less work plugging in numbers. Okay, there's no substitution needed here. What we're going to do is we're going to expand. But I'm going to expand this top to a certain point what point am I going to expand it to? I'm going to expand it until I get to the largest of whatever these I happen to see. I'll show exactly what I'm talking about. Okay, I'm going to expand this 7 factorial. I know that it's going to be 7 times the number before it, which is 6, times the number before that, which is 5. But I'm going to actually stop there, and I'm going to just add in my factorial, which is cool because I know that that's saying times 4, times 3, times 2, times 1, which fits with what I'm doing up here. So that's fine. But there's a reason for doing it this way. Remember, I told you I'm going to stop at the largest of these two that I see. So I'm going to write 5 factorial. This one, the smaller one, I'm going to write out. So we still have 2 times 1, right? 2 factorial is 2 times 1. Now, why did I take a second to write it out that way? Well, because this 5 times 4 times 3 times 2 times 1 and this, which is the same thing, we can actually eliminate right away. Okay, that's why I write the expansion that way. A lot of people do it that way. Okay, then I can notice, for example, this 2 and this 6, I can start to reduce. That's also why I expanded my other value, my other factorial. So the 2 and the 6 will reduce. That becomes a 3. So what am I really left with here? I have 7 times 3, which is 21, and then I'm left with just 1 on bottom. So 21 is the answer here. Let's check one out with n's rather than numbers. Okay. Here's what we have. N times the number before it, which would be n minus 1, times the number before that, which would be n minus 2. And we could go on for a long time doing this, right? But we know that we're just using all the numbers beforehand. So I'm going to put a factorial here, because that's telling me keep on going. N minus 3, n minus 4, right? Here, if I expand this n minus 1 factorial, right, that'd be n minus 1 times n minus 2, and I would keep on going as well. And again, what do I notice? My n minus 2 factorial shows up twice, so those are going to eliminate. And in fact, my n minus 1 not factorial, but the n minus 1 also shows up twice. So if I have n factorial over n minus 1 factorial, really, it's just equal to plain old n. Okay, so there are 2 here for you to try. One of the ones with just regular values, one with an n value. So try these out, pause the video, and resume when you're ready to check your solutions. Alright, so I'm going to expand this 12 until I get to 9 factorial, but I'm also going to expand this 4 factorial. So here's what it looks like. We've got 12 times 11 times 10 times 9 factorial. And then we got 9 factorial, and I'm going to expand this 4. 4 times 3 times 2 times 1. Now, the 9 factorials, those went away. No problem there. As far as the rest of this stuff, 4 times 3 is 12. So this 4 and 3 I can eliminate with the 12 really quickly. Okay, because they multiply and they add. I'm sorry, they multiply to the same number, not add, multiply. Okay, so that's one way of getting rid of that 12. Then we got this 2 left over, and I see an even number 10, so I get rid of the 2. 10 divided by 2 is 5. So what do we have left on top? We have 11 times 5 on top, which is 55. I've successfully eliminated everything from the bottom except for the 1, so 55 divided by 1 is just plain old 55. Let's check out this other one that you had. I'm going to expand 5 factorial until I get to 3 factorial. So 5 times 4 times 3 factorial. I'm going to expand this, and I'm going to be adding 1 less each time. So you've got n plus 2 times n plus 1 times plain old n. I'm going to stop there because I notice that I have a plain old n. So that's where my factorial will go in, because remember, I'm doing all the numbers before n as well. And here we have 3 factorial and n factorial. Now let's see what goes away. 3 factorials, and then we've got n factorial going away there. Okay, that's not bad. We have 5 times 4, which is 20, times n plus 2 times n plus 1. That's it. Nothing else. So that one was probably a little bit trickier. You might not have known where to stop on that one. Hopefully you got this one though. Now we needed those factorials because they're going to show up in the binomial theorem. Here it is, the binomial theorem. What it says is that in the expression of x plus y to the n power, notice how we expanded it. All right, we have x plus y to the n. You're noticing all the things that have happened before, right? Like we have our power of n, and then it's decreasing by 1, and all of a sudden y shows up. So all this stuff works the way that it should, okay? But then you see this strange thing right here. This is called, well, this is a coefficient, the n CR. This is called choose. Okay, it's going to help us with combinations. But we need this thing right here. Okay, notice how n choose r shows up as our coefficient. In order to do n choose r, we're going to be doing n factorial divided by n minus r factorial times r factorial. It's also mentioned that we can rewrite n choose r in this way. Kind of looks like a fraction just with no division sign. So you're going to see that happening in the examples down here. Okay, so this is the binomial coefficient, n choose r. This is the formula we need to use. So in your example problem, it says find each binomial coefficient. So we're doing, for the first problem, 10 choose 4. 10 is my n value, 4 is my r value. So when I plug it in, we have 10 factorial over 10 minus 4 factorial times 4 factorial. 10 minus 4 is 6. So when I expand this top, I'm going to stop at 6. 10, 9, 8, 7, 6 factorial. 6 factorial, and then we'll write out 4, 3, 2, and 1. Okay. Again, we notice that the 6 factorials will eliminate. And then we want to start getting rid of some other stuff, right? 4 times 2 is 8. So I can get rid of the 4 and the 2, and that eliminates my 8. And then here I've got a 3, which I know can go into my 9 3 times. And that 1 really doesn't matter. So what do we have left? We've got 10 times 3, which is 30, times 7, which is 210. On bottom, we're left with just 1. So that's our solution. Let's check out another one using this combination. This time we're doing, that's a 5. It's tough to see, but that's 5, choose 3. So this is our n value on top, 5. We need to do 5 minus 3, right? N minus r factorial, and then 3 factorial, right? N, r, that's where all that stuff goes. So let's see. That gives us 5 factorial. 5 minus 3 is 2 factorial. So remember, I want to expand this 5 until I get to the larger of these two. So I'm going to stop when I get to that 3, right? 5 times 4 times 3 factorial. Let's see, I'm going to reorder this for my 3 factorial first, and then I'm going to expand 2 times 1. Okay. And then we notice that some stuff eliminates. 3 factorials, those go away. 2 goes into 4 twice. And what we're left with is 5 times 2, which is 10. Okay, so that's how your n choose r works. That's the binomial coefficient. So I've got 2 here for you to try out. I'm going to leave these up for you to use as a reference. You're going to try those ones on your own. Pause the video and resume it when you're ready to check. All right, let's see. We want for this first one 9 factorial over 9 minus 3 factorial times 3 factorial. Rewriting that, that's 9 factorial over 6 factorial times 3 factorial. So that's where we're going to expand our 9 to. 9 times 8 times 7 times 6 factorial. 6 factorial, and then I'm going to expand to 3. 3 times 2 times 1. That's where our factorials cancel out. Let's see, 3 is going to go into 9 3 times. 2 will go into 8 4 times, and now I can multiply. Let's see, 3 times 4 is 12 times 7, that's 84. And we've got 1 on bottom. So hopefully you got 84 for that one. The second one you had was written the other way, right? We have 7 as our n value, 7 minus 2, which is our r value, and then 2 factorial. So let's see, 7 factorial over 5 factorial times 2 factorial, right? That becomes 5. So I got to expand this till I get to 5. So 7 times 6 times 5 factorial, that was easy enough. Okay, so let's see what goes away. 5 factorial. This 2 is going to go into 6 3 times. I'm now basically done eliminating from the bottom. 7 times 3 is 21. So hopefully you got those 2 answers for those binomial coefficients. Alright, now we're going to actually use that n choose r x to the n minus r y to the r weird looking thing that was in that binomial coefficient that we saw in the last page. Okay, this thing. We're going to use this. Okay, something we have to keep in mind though, because we have n plus 1 terms, the rth term, I know it sounds funny to say rth, but the rth term, what they're looking for, will require us to use r minus 1 for r. Okay, pay attention to these problems. These are a little weird from some stuff that you've done before, so keep that in mind. Okay, we want to find the 5th term. Right, this would be our rth term, the 5th term of a plus 2b to the power of 8. That's an 8 right there. It's a little tough to see. But we need to know some things, right? We need to know, for example, that our r value is going to be 1 less, right? 1 less than whatever they give us. So 5 minus 1 would be 4. So that's our r value is 4. I also really don't like these a's and 2b's. So we're going to just replace it with x's. So a will be x right now, and y's. Y will be 2b for right now. And we'll substitute those back in later. The last thing that we need is our n value, which is up here. They give it to us as 8. The formula says n choose r times x to the power of n minus r times y to the r. So if we just fill in basically all those values, right? N we said was 8, choose 4 is our r value. X to the power of 8 minus 4, and then y to the power of 4. Now, we've got to work on this piece first, and then we'll sub in these values after. But let's take care of this. 8 over 8 minus 4 factorial times 4 factorial. So 8 factorial over 4 factorial times 4 factorial. So I got to expand this to 4. 8 times 7 times 6 times 5 times 4 factorial. I'm going to leave one of them alone and expand the other. 4, 3, 2, and 1. Because just like before, we see our 4 factorials disappear. Let's see. 4 times 2 is 8, so those go away. And let's see, that 3 is going to go into 6 twice. So let's see, on the top I've got 5 times 2 is 10, times 7 is 70, over 1. So we got 70. So this 8 choose 4, we found it to be 70. X is 8 minus 4, so it's going to be x to the 4th power, and y is also to the 4th power. That's great, but we have a little bit of a problem because we've got to substitute in the values for x and y now. So let's see. 70 stays. X we said is a to the 4th. Y we said is 2b, right? 2b to the 4th. This would be fine, except that we have this 4 that's got to distribute to each of these terms. And then we can multiply the 70 and whatever that becomes. Okay, so let's see. 78 to the 4th. 2 to the 4th. Let's see. 2 times 2 is 4. Times 2 is 8. Times 2 is 16. B to the 4th. Now I have numbers that I can multiply comfortably. 70 times 16. I can either do that in my head or on the calculator. That's going to be 1,120 times a to the 4th, b to the 4th. Yes, that was a lot, but let's quickly just go back through it, right? They gave us the term we're looking for, the 5th term. We needed to find our R value as 1 less, so we got 4 here. We replaced these A and B values with X and Y, just make it a little bit easier for the time being, and our N value they gave us to is 8. We plugged it into this formula, the same formula right here. We figured out the N choose R value, which was 70, and then we replaced X and Y with A and B and did any kind of distribution necessary. Okay, so we're going to try another one right here. We want to find the 4th term of P plus 3Q to the power of 6. So the R term is going to be 4 minus 1. So our R term is going to be 3. I'm going to replace X with P. Y will be our 3Q. And N here is 6. So I'm doing 6 choose 3. X to the 6 minus 3, y to the 3. So I've got to take care of this 6 choose 3. I skipped a little bit. I know 6 minus 3 is going to give me 3. So when I expand this, 6 times 4, 5 times 4 times 3 factorial, over 3 factorial times 3 times 2 times 1. Okay, our 3 factorials are going to cancel. 3 times 2 is 6, so those cancel. So we got 5 times 4, which is 20. And over 1. So that's our binomial coefficient, 20. X to the power of 3, y to the power of 3, and then we're going to replace. X we said is P, so that's 20 P to the 3rd. Y we said is 3Q to the 3rd. So we've got to distribute 3 to the 3rd and q to the third. 3 to the third, 3 times 3 is 9, times 3 is 27. So now I'm going to be multiplying my 20 times my 27. Let's see, 2 times 27 is 54 plus a 0. So that's 540 is my coefficient. P to the third, Q to the third. Oops, that's a Q, not a P. Okay, so there's one here for you to try out. Pause the video and resume it when you're ready to check. All right, let's check this one out. All right, we have our R value here. Will be 5 minus 1, so our R value here is 4. X will be 2h. Y will be 2k. And our N value here they give us as 7. So we need to do 7 choose 4, x to the 7 minus 4, y to the 4. Let's take care of the 7 choose 4 thing first. 7 factorial over 7 minus 4 factorial, 4 factorial. So let's see. 7 factorial over 4 factorial times 3, right? 7 minus 4 is 3. So I've got to expand this until I get to 4 factorial. And I'm going to expand my 3. The 4 factorials go. 3 times 2 and the 6 go. So let's see. 7 times 5, that's 35. And I have only one left on the bottom. So that's the coefficient, it's 35. Let's see. X, we said, is 2h. 7 minus 4 is the third power. Y, we said, is 2k to the fourth power. So we've got to distribute. We also have to do that here as well. So let's see. 35. 2 to the third is 8. 2 to the fourth is 16. And these are the numbers we want to multiply. 35, 8, and 16. If you use the calculator or if you did it in your head or on paper, whatever, you're going to get 4,480. That's your coefficient. Then we got h to the third, k to the fourth. Those are difficult. They are. Hopefully you got those. If you didn't, maybe you can rewind the video and go back and look through, maybe identify where you made your error. Okay, we've got one more thing to look at, which is way easier. Okay, this is something called Pascal's triangle. This is something that you might have done as a kid and just didn't realize it, but what Pascal had ended up doing was he made this little triangle, right? He had 1, and then he did 1 plus the number on top, which would be 0. So we got 1 and 1, and then he would have added, okay, I got a 0 here and 1, that gives me 1. But the more interesting thing happens in the middle. When we add these two, we get the number directly below. So this is how Pascal's triangle works. Okay, if I add two numbers directly next to each other, they're going to give me the number in between. Okay, for example, down here, if we did 4 and 6, when we add those, it gives us that 10. Okay, so you can see it happening all over the place in this, right? You can see it happening here, the 1 and the 4. When we add them, they give us that 5. Okay, but what's really interesting, and it's not a coincidence, is if we look at each of these rows, right, the 0th row, the 1st, 2nd, 3rd, 4th, 5th, all the way down, you notice that it actually matches the triangle, the expanded form that we looked at the beginning of this unit, right? What matches specifically are those coefficients, right? Here's the expanded form. You can even go back to the beginning of the video if you wanted to check it to believe me, or you can look at your notes, right? These are all the numbers that we came up with, and if you notice, they match on Pascal's triangle. So what does that mean? Instead of having to expand and do a whole bunch of work to figure out these next couple of digits, we know how this pattern works. All we have to do is start with a 1, add the next 2 to get the next digit, add these 2, get the next digit, add these, get the next digit, right? And then we know that our x is going to be going down in power and our y's go up. So we can actually find out quite a lot of these using Pascal's triangle. So this is the last thing that we're going to do. We're going to use the 5th row of Pascal's triangle to find the binomial coefficients, just the numbers, of the 6th row. Now, they already gave us the 5th row. It was 1, 5, 10, 10, 5, and 1. So if I want the 6th row, automatically I know I start with a 1, and then I'm going to add these next two numbers. 1 and 5 is 6. Then I'm going to add these two numbers. 5 and 10 is 15. Then I add these two. 10 and 10 is 20. 10 and 5 is 15. 5 and 1 is 6. And then I got to drop another 1 at the end. Okay? It should be symmetrical, which it is, right? 1, 6, 15, and then at 20. So, oops. Missed one. That's your 6th row of Pascal's triangle. Your problem asks you to find the 7th row. So you need this that we just found. You're going to find the binomial coefficients for the 7th row. You're including that 1. I'm sorry that I chopped it off. All right, so here's what we had for the 6th. Right, 1, 6, 15, 20, 15, 6, 1. We know that we're going to have the 1, and then we got to add each of these. So 7, 21, 35, 35, 21, 7, and 1. That is your 7th row. And that is the end of the lesson. Longest lesson so far. Give yourself a hand for making it all the way through. You learned a lot of different things here. Some of them easy, some of them difficult. So be proud of yourself. We're going to move on to a lesson about the counting principle next. So we'll probably end up seeing that n factorial again. So I'll see you there at lesson 5. Bye.